Finding the greatest common divisor, or the GCD, of two numbers is an important thing in math. And if the numbers are small enough, it's not so hard. It's not so hard to do. Like, for instance, greatest common divisor of 28 and 36. You could just sort of list out all the ways of making 28. And list out all the ways of making 36. And inspect these numbers that are all divisors or factors of the number and say, well, of these numbers, they have in common 1, 2 is a common factor, 4 is a common factor. Of those common factors, 4 is the largest. So we say that the GCD of those two numbers is 4. Sometimes in math they write it this way, 28, 36. That's notation for that in this type of math. So that's fine if the numbers are small enough. An alternate way of doing it is to do the prime factorization of each number. And write each number out as prime factors. And then look for what prime factors they have in common. They both have 2's. And you take the one with the smaller exponent, since that goes into both numbers. In this case, they both are 2. So 2 squared equals 4 is the GCD. So that's fine if the numbers are small enough. But what if the numbers are large? For instance, find the GCD of 13,561 and 12,797. So the factors of those are not obvious at all. I'm going to show you something called the Euclidean Algorithm, which finds the greatest common divisor without finding either the factors of either of the numbers. I'm going to make a chart, and the chart is going to have 3 columns: the bigger, smaller, remainder. And what you do is you start by putting 13,561 is the bigger number, 12,797 is the smaller number, and on the side you divide. 1297 is a 13,561. It goes in one time, and the remainder is 764, and the remainder goes here. In the second row, the bigger number for the second row is the smaller from the first row, so everything moves over. So 12,797 is the new bigger number. The remainder becomes the new smaller number, and again you divide now the smaller into the bigger, 12,797. Some calculators have a remainder button on them. Even if it doesn't, you can divide with the calculator and see that it's 16 point something. Then you can do 16 times 764, 12, and then subtract to get 573. Again, the smaller becomes the bigger, the remainder becomes the smaller, and we divide again. It goes in one time. Remainder 191. And again, the smaller becomes the bigger, the remainder becomes the smaller, and we divide again. And it seems like it could go on forever, but it will eventually stop, because eventually I will get remainder 0. And when I do, the answer is the previous remainder. And this is true. Those two numbers are that 191 goes in to both 13,561 and 12,797. That's how to do the Euclidean algorithm, and in another video I will show why this works.